In this paper, we propose Spike-EVPR, an event-based visual place recognition pipeline with cross-representation aggregation networks using deep spiking residual network. Visual place recognition is a very challenging problem in the field of computer vision and mobile robotics. It can be used for augmented reality in 3D computer vision and loop closure detection in SLAM. At present, researchers have attempted to deal with two main challenges using spiking networks for EVPR. First, how to compress event data to generate representations that fit the spiking networks is an issue that needs to be solved. Event streams have rich timestamps, but directly feeding event streams into spiking networks will lead to high network training costs. Moreover, event data is highly spatially sparse at a single time step, which hinders the spiking network's capacity to encode spatial neighborhood information of the scene. It is difficult for a single representation to make full use of event data for EVPR tasks. Therefore, multiple representations may need to be designed. For EVPR with complex scenes, shallow spiking networks may not be competent, and deep spiking networks need to be designed to obtain robust global feature descriptors of scenes. Thus, upon acquiring compact spike event representations, the subsequent challenge is how to construct a deep spiking network to fuse multiple representations and fully exploit discriminative features efficiently. To deal with the aforementioned challenges, we propose Spike-EVPR, a novel descriptor extractor pipeline for large-scale EVPR tasks based on deep spiking residual network architecture with cross-representation aggregation, and the whole pipeline is shown in the video. In our Spike-EVPR, the leaky integrate and fire neuron is predominantly used, which is also a commonly employed spiking neuron in spiking networks. Firstly, we introduce two event spike representations, which are specifically tailored for spiking networks and designed for EVPR tasks: the multi-channel spike tensor and the time surface spike tensor. In the first part of our network, named Bifurcated Spike Residual Encoder, event volumes are processed to two event spike representations. Then, the two spike representations are fed into our BSR-Encoder to obtain basic feature maps. In the second part, named Shared and Specific Descriptor Extractor, we obtain shared and specific spike descriptors through SSD-Extractor, which takes into account the characteristics of the output spike feature maps. Considering the diverse information harbored by the various descriptors and their disparate contributions to the final global descriptor, we next introduce the Cross-Descriptor Aggregation Module to autonomously learn and selectively emphasize vital information from different descriptors, thereby enhancing the model's performance and generalization capabilities. To evaluate the performance of the proposed method, we conduct experiments on Brisbane-Event-VPR and DDD20 datasets. Experiments demonstrate that our Spike-EVPR outperforms other EVPR methods, including AN-based and SNN-based SOTA methods. On the Brisbane-Event-VPR dataset, on average, the recall at one of our DS-EVPR is 7.61% and 20.07% higher than the AN-based and SN-based SOTA method, respectively, on the DDD20 dataset. Our method is 13.2% higher than the AN-based SOTA method. As discussed in our paper, our Spike-EVPR, RED, performs better than SOTA methods under most scenes. These are retrieval success rate maps of Event-VPR and Spike-EVPR. These are matching matrices between databases and query of Event-VPR and Spike-EVPR. We also explore the impact of different network components of our Spike-EVPR. The results illustrate that each component plays an important role in improving the network performance. In conclusion, the main contributions of this paper are as follows. Thanks for watching.